Hey guys, welcome back to Dynamics, everyone's favorite subject. So today we're covering problem 5.B.7. This problem is pretty simple. It's a pin with a rod and a wheel attached to it, basically over nothing as you hold it steady. So for this, your free body is pretty simple. Since you have two masses, the rod and the wheel, you need two free body diagrams. Only forces on that is something just going to be the weight force, both going in the negative j-hat direction. Coordinate system is pretty easy, just match up to how it is to begin with. No fancy trigonometry equations required. You guys know the next step, so they take your forces, write them on vector form. So that's weight force, it always goes down, so it's just going to be the weight force in the j-hat direction. Next up is the acceleration. It's an acceleration at g, which is at any of the mass centers, basically. Any way you want to put on the body doesn't really matter. Next up is Newton's equation, force equals mass times acceleration at whatever mass center you choose. Again, it's pretty simple. You have two of them, and it just ends up equaling this. Next up is momentum. For momentum, we're choosing case 1, where we have the acceleration of alpha at the mass center, which allows us to clean up and make it look a lot nicer. For this, for the I and for the K, you simply just break up into the two component forms to make it easier to plug in all your other variables later on. You guys know these next steps. Do all the tables. Tables for kinetic, potential, and non-conservative forces. For this problem, it's stated that first we were at rest. The key word there is at rest. That means your kinetic energy at state 1, automatically 0. Now, potential energy for state 1, it's also 0. Simply because you can choose where you want your potential energy to be 0. Easiest place, straight down the middle of this whole body. Ends up equaling 0. And of course, when you release it from rest, it's going to pick up kinetic energy. It's now going to technically lose potential energy, since it's now dropping below the point you chose as your 0 reference. Now for RG, we simply put it here at the 0.3L. So for your potential energy, it's going to look a little bit different for the mass of the rod, depending on wherever you decide to put the G. And then M is just at the full, for the wheel, it's at the full length of the 0.3 plus the 0.7. For this, there's no conservative forces. This is a body, technically in free fall. If you have friction anywhere near this equation, you've done something horribly wrong and you should go check that back out. For step 10, it's pretty simple. It's assembling your work energy equation. We know kinetic energy is 0 for state 1. Potential energy is 0 for state 1. You don't have any conservative forces. So this whole entire left side of your equation will be 0. Only thing you have left now is your kinetic energy for state 2 and your potential energy for state 2. So I'm going to just plug it in, and this is what you end up getting. Now we do need technically 1 but 2 equations of kinematics. All we simply need is the velocity for the rod and the velocity for the wheel. That's pretty simple. All it is omega times the distance. So it's omega times 0.3 and omega times point L. Once again, that 0.3 is because we put RG here at that 0.3 spot. So simply take the equation we have for work energy, which is 0 equals all of this. Anywhere where you have a velocity, anywhere you have a velocity, simply plug that velocity in now with these. Solve that whole thing first symbolically. Your next step will be taking all your variables you were given, plug it into your equation. From there, just simply solve for omega. And omega, in our case, ends up being 4.021 radians per second.